Thank you very much. Actually, when Lars first asked me whether I would be willing to give a presentation today, he was already quite specific on what he wanted me to do, and I liked that. He asked me to talk about my work and present a new method. That should include a summary of the advantages and the disadvantages of the method, and I should include a note on how the method could be applied in educational research. So I want to make sure that I address each of these points, so I was thinking I start with this. I will present a new method, and that is continuous time modeling as a dynamic approach to the analysis of longitudinal data. The advantages of continuous time modeling, it's dynamic, and as I will try to argue in the following, I think dynamic models get us closer at the mechanisms underlying change processes as compared to static models. And it's continuous time, and as I will also try to argue in the following, most of the processes we're dealing with in education and in psychology are actually developing continuously over time: motivation, cognition, emotion, and we only happen to use discrete snapshots in time to observe them. So we shouldn't take these discrete snapshots in time for reality, but rather try to infer the underlying continuous time processes based on these discrete snapshots. So that's what continuous time modeling is about. The disadvantages of the model and of continuous time analysis, it's dynamic and it's continuous time. Dynamic meaning that our models and the interpretation of the models typically gets a bit more tricky because we're dealing with reciprocal relationships, for example. So it's not as easy as it is in regression analysis anymore. And it's continuous time. That means we typically have to deal with differential equations, so the math gets a little bit more complicated. But I'm trying to convince you in the following that it's worth the effort, because I think continuous time modeling may help us to better track, and maybe more importantly, to better understand the mechanisms underlying educational progress and psychological development in general, for that matter, at the group level, so when it comes to panel data, as well as at the individual level. And that's more or less my presentation. Everything that follows are just a bit more elaborations on each of these points here. So let me begin by being a bit more specific on my terminology, and let me say a little bit more by what I actually mean by dynamic. What is dynamic, and why should I care about dynamic models? And for that, let me begin with a very simple example. The probably most simple model you can think of, just two variables, set and y, purely cross-sectional. We're regressing y on set, so we get a standard regression equation like this one, across individuals I. And as you all know from the very first statistics course, we now have two different options of interpreting this parameter a. We can either interpret it as a causal effect of set on y, or we can interpret it just as a relationship between the two variables. Which of these interpretations is correct is not a question of the statistical model, but it's a question of the underlying research design. If set is an actively manipulated variable with a random assignment to two different groups, then the evidence for causal effect A will be quite high, whereas if set and y are just two arbitrarily measured variables, then the evidence for causal effect will likely be low. Now, what happens when I move from this design, cross-sectional, to a longitudinal design by simply replacing the variable set by the variable time? And that's what we do, as Asko has told us, for example, in multi-level modeling or in growth curve modeling, where we regress y on the variable time. So A may now be a fixed effect, or maybe a random effect across different individuals, but the crucial point is that now we no longer have two different options of interpreting this parameter A, because here A will never be a causal parameter. Because by the very definition of a cause-effect relationship, the cause has to precede the effect in time, and with time itself being the proposed cause, that doesn't work. Put somewhat more eloquently than I can do it, here's one of my favorite quotes by Paul Baltus and colleagues, who said that although time is inextricably linked to the concept of development, in itself it cannot explain any aspect of developmental change. Time, rather like the theatrical stage upon which the processes of development are played out, provides a necessary base upon which the description, explanation, and modification of development proceed. So when we're really interested in the mechanisms, in the psychological mechanisms underlying change processes, then maybe we shouldn't focus so much on these kinds of models, but maybe we should have a look at these kinds of models Asko was also talking about, where we're looking at the relationship between variables and the development of these variables across the dimension of time without time being the causal variable in these models, like the standard vector autoregressive cross-select models we've heard about in the previous presentation. So depending on the role of time in longitudinal models, we can at least very roughly distinguish between two broad classes. On the one hand, the class of models where time is considered explicitly as a predictor, as a causal variable in our model, as it is the case in growth curve modeling, multi-level modeling, and so on and so forth. And here I speak of static or descriptive models. And models where time is only considered implicitly by the order of the variables, but not explicitly as a causal variable, as it is the case in autoregressive cross-select models, p-technique, dynamic factor analysis, and so on and so forth. And here I speak of dynamic or explanatory models. Now, what I would like to do in the following, I would like to focus on these class of models, because even though these models are extremely useful when it comes to the detection of the underlying mechanisms, the way they are currently being used in the majority of research, I would argue, is at best maybe somewhat suboptimal and at worst really wrong and yield wrong conclusions and wrong parameter estimates. So why is this? Why am I saying this? What's the problem with dynamic discrete time models? And for that, let me give you again a little example. And imagine we have a researcher. And this researcher, one, is interested in the relationship between two variables, x and y. He conducts a longitudinal study across many time points, and he used a time interval of, say, 1 month, or 1 year, or 1 minute. The unit doesn't matter. And he obtained these results. Now let's imagine we have another researcher who did exactly the same study, with the only difference that this researcher used a time interval of 2 months instead of 1. And he or she obtained these results. Now clearly the results are not the same. The autoregressive parameters are a little bit lower, the cross-select parameters are a little bit higher here. And at that point you can already imagine the debate in the scientific community who of the two researchers is correct. And can we compare these parameters at all with each other, given that they are based on different time intervals? And I'm saying this not least based on the Science article which came out last month on the reproducibility of psychological findings. I mean, what does it mean for the production of cumulative knowledge in psychology or in education if we're not even able to compare studies which were based on different time intervals? And of course, that's a great simplification of reality. In reality, we're dealing with much more complicated models, as we have also heard in the previous talk, with dynamic error terms, with measurement error terms, with latent variables. But the crucial point is that time intervals may not only vary across different studies, but they may also vary within one and the same study. We start out with 1 month intervals, then we have 2 month intervals, then we have a 1 year lag, for example. And even that's a great simplification of reality, because in reality, time intervals may not only vary across studies, within one and the same study, but also across individuals within one and the same study. And these time intervals may come out of any known or unknown distribution. So in the extreme case, we have a situation of, say, 10 time points, 100 individuals, so we may end up with 900 different time intervals. And all of these different time intervals will have a complex nonlinear effect on our parameter estimates. And at that point, going ahead and saying, well, they're probably equal, so let's ignore the problem, that's usually not a good idea. So what's the problem? The problem is that we have a powerful class of statistical models, in the broadest sense, vector autoregressive cross-select models, where the information on time simply got lost. What's the solution? The solution is we need to get time back into these discrete time models, and that's what continuous time modeling is about. So what I would like to do in the following, I would like to introduce you to the basic idea of continuous time modeling, and I would like to do so in 3 steps. I will start with what I call an intuitive approach, because I hope it gets you, if this is the first time you're exposed to it, I hope this gives you an intuitive feeling of what it does, even though I'm mathematically not really precise here. Then I will introduce the exact approach, where I'm precise, and then we will also have a quick look at the math behind all of this. But let's start with the intuitive approach. What we see here is, again, the standard vector autoregressive cross-select model. X is a vector of an arbitrary number of variables observed at time point t, and this is a discrete time point. That's what this I is indicating. So for example, t may be the year 2012, and if this is the third wave in a panel study, then I would be 3. I can regress x on the previous time point, but now in this notation, I'm very explicit that these two time points are separated by the time interval delta ti, and it's a discrete time interval. So because of this, my parameter estimates here are a function of the length of the time interval. And that's the problem. My parameters depend on the length of the time interval. What I would like to have, however, are parameters that are independent of the length of the time interval in order to compare them across different studies or across different individuals. And one very simple idea one could come up with, and that's an idea one actually came up with only in a very different context, and that's in the context of latent change score modeling, is to say, well, maybe let's not predict x directly, but let's rather predict the change in x. And let's divide this change of x by the length of the time interval between these subsequent measurement points. So now we're predicting a rate of change. And because we kind of control already for the length of the time interval here, I can now regress this on the previous time point. And since I control for it, now I get parameters which are no longer dependent on the length of the time interval. So a very simple idea. I just give these parameters a very fancy name, and I call them approximate drift matrix here. Now, with this very simple idea in mind, we now have a way to relate these discrete time parameters, which are a function of the length of the time interval, and these quasi-continuous parameters, which are no longer a function of the length of the time interval. We can equate these two equations, solve for the relationship, and when we do so, we get this very simple relationship here. So now we find a way to translate discrete time into quasi-continuous time parameters. And with that in mind, we can reconsider our intro example again. Remember, we had two researchers, one a 1-month interval, the other a 2-month interval. Here I'm just looking at the autoregressive effect. And now we can plug in the numbers. 0.64 minus 1 divided by 1, 0.41 minus 1 divided by 2. And when I do so, we note two things. The first thing is the coefficients get negative. They get negative because I subtract 1, or the identity matrix, in the numerator. So the closer to 0 these coefficients are, the more stable in the sense of rank order stability the parameters are. The second thing I note is that my substantive interpretation just reverses. If I would ignore time, I would say, yeah, 0.64 is higher than 0.41, so obviously researcher 1 deals with a more stable process than researcher 2. Now taking the difference in the time interval into account, I come to exactly the opposite conclusion, that it's actually study 2, or researcher 2, which observed a more stable process than researcher 1. So that's kind of the intuitive idea what continuous time modeling does and how it relates the discrete and the continuous time parameter with each other. Mathematically, we can do this a little bit better. Mathematically, we wouldn't take the difference and divide by the length of the time interval, but we would rather take the derivative of x with respect to time and regress this on x. So now we're dealing with a differential equation. X is a function of its own derivative, but it's a very simple one. So we can easily solve this differential equation, and the solution of it is the exponential function, now with the exact drift matrix in the exponent. In exactly the same way as before in this intuitive approach, we can now relate the discrete time parameters to the underlying continuous time parameters, but now in a mathematically exact way, and that is exactly this matrix exponential relationship here. So again, now we have a way of exactly relating the underlying continuous time parameters to the discrete time instantiations for a given time interval delta t. And that's really the essence of continuous time modeling. There's not much more to it. The rest is just math and some extensions of the basic model in various directions. And nevertheless, for everyone who's interested, I would give you at least a quick insight into the math behind it, because even the math behind it can be summarized in 6 simple steps, even though the equations look on first sight a bit daunting. So let's open this box for a moment, and then we will close this box again. If we open it, we start again with the standard discrete time autoregressive cross-select model. That's the part which we have already discussed. Now it's just augmented by an intercept, and we do have an error term in here. And I just note this is a basic model, so we can extend this in various directions with trait variables, with input variables. So this is just the basic version. In the second step, we formulate the underlying continuous time model by taking the derivative with respect to time. That's the part which we have already discussed. Here it's just some extensions with the error term. As before, I take the solution of this differential equation, and in a fourth step, I constrain my discrete time parameters in the first step to the solution of the differential equation in step 2. That's what I'm doing here. That's the part which we have already discussed. I'm constraining the discrete time parameters to the solution of the differential equation to the underlying continuous time parameters. That's what I do here. And now all I need to do is I need to set this model up, for example, as a structural equation model. So I just take my RAM matrices or my literal matrices or your favorite notation and just impose these constraints at the right places in the matrices. And then I can use any standard fitting function, like standard full information maximum likelihood estimation, to obtain my parameter estimates. And that's really all we do under the hood. So let's close this box again. Because from a user's perspective, this is the stuff you don't have to worry about because of this guy here. And that's Charlie. And I think Charlie is probably joining us in from the HU site. Charlie is a PhD student of mine, and he essentially told Han and me that our original functions, which we called CTSEM for continuous time structural equation modeling, were crappy, and that he can do it better, and he did. So he created the new CTSEM version, which is an R and OpenMX-based package for continuous time modeling. It's open source, freely available, thanks to Charlie, now on Crane. So I encourage everyone to just try it out. And what I would like to do in the following, I would like to give you a little example on how we can implement such continuous time models via CTSEM and how we can also interpret the parameters. And that's what I'm doing with empirical data, which we used before in some of our work on the group-focused enmity study. That's a large panel study, 2,700 individuals at 5 different time points, and you can already see the time intervals are not equally spaced. And just for the purpose of illustration, I'm focusing on 2 constructs, anomia and authoritarianism, and I'm interested in an old sociological research question, whether higher levels of anomia lead to higher levels of authoritarianism, or whether it's just the other way around. The data structure, and Asko has already talked about it. We're also using wide format, so I will go over this quickly. We just have the time intervals in the last variables. So we have 5 time points, that is 4 time intervals. And here you see very simple example because everyone has the same time intervals, but of course they could be individually varying. So for each individual, we could have a different time interval in here. The setup in CTSEM works via 2 functions. First, via CT model, we define the actual model. And then with the CT fit function, we combine the data and the model with each other. And you see there are lots of different options. And then we can use the standard summary and plotting functions in R to see our results. The results will look a little bit like this. And somewhere in the output section, you will find this drift matrix again. The drift matrix showing the relationship between these 2 variables over time. And now remember, the auto effects, the closer to 0, the more stable the process is. So we can see here that for authoritarianism, closer to 0, we're dealing with a more stable process than for anomia. And with the cross-select effects, again, the usual way around, and we find that the effect of authoritarianism on anomia is somewhat stronger than the other way around. And these are the parameter estimates which are independent of the specific sampling intervals we were using. So these are parameters we can always interpret and compare across different studies. Now, the best way to understand these parameters is probably to plot them. Given this drift matrix, I can now see how the discrete time autoregressive parameters or cross-leg parameters change as a function of the length of the time interval. And here you see they change dramatically as a function of the length of the time interval. Depending on where we look, the differences will be very small or quite large. And the same is true for the cross-leg parameters here. And here strange things may happen. These curves may even cross each other. So for one time interval, I may conclude, yeah, it's A that leads to B. For another time interval, I would conclude that it's actually B that leads to A. And that's not because causality magically reversed, but because it's a function of the length of the time interval I'm looking at and some other factors. So again, I hope this illustrates that it's extremely important to take the length of the time interval into account in your analysis and in the interpretation of your data. Okay, so that was continuous time modeling in a nutshell, and we have seen continuous time models account for different time intervals, and that's great, but is there more? Are there any other reasons why I or you should care about continuous time modeling? And I think yes, I think there are plenty, but since I don't have plenty of time, I will just focus on two conceptual and two technical points. One conceptual point is that I think just thinking continuous time may offer new perspectives on the way we think about missing values and the way we think about our study design. And along the way, on the technical side, I just note that we can also use it to model damped and or coupled oscillating processes in exactly the same fashion. And then I think it may also offer new ways to integrate between and within person research. And along the way, I just note that everything I'm saying here also applies to the n=1 individual level in the same fashion. And also the same program can be used for that. So considering the time very quickly, let's have a look at what I mean by offering a new perspective on missing values and study design. And when I talk about new perspectives, I should probably first say what's the traditional perspective. And the traditional perspective on missing values, at least to my understanding, goes a little bit like this. We plan a study, for example, with 8 time points, and then for whatever reasons we cannot realize some of these time points, so we have missing values. Either entire waves are missing, or at the individual level that a certain individual didn't show up. Now we have missing values, and we kind of have to deal with this, and there's lots and lots of work on this. The continuous time perspective starts from the other side. Here we're saying there is an underlying process. This process may have a certain function. It may be, for example, this oscillating function. And now I'm trying to get information about this underlying function. So I take samples. I take samples in time. And the more samples in time I take, the better, because the more information I have about it. I like to think about this perspective as a perspective for the optimists among us, because instead of focusing on what's not there, the missing values, and trying to deal with what's not there, here we focus on what's there, our observations, and we're asking the question whether what's there allows us to make inferences about an underlying process. And I think the advantage of this perspective becomes obvious when we're trying to apply the traditional perspective to continuous time processes. Because in that case, it's not so simple that we simply have 3 missing waves here, but if we're dealing with a continuous time process, all of these measurement occasions are missing. In a continuous time process, we always have an infinite number of missing values. And at that point, you may argue, yeah, I mean, he shows us a nice way to look at the world, but it doesn't change anything. I mean, the situation is exactly the same. And I would agree with this. I'm just showing you the other side of the coin. But I think looking at the other side of the coin may be helpful in the way we think about the design of our studies. Because instead of focusing on having a study design where we minimize the amount of missing values, maybe we should have a look at designs which maximize the amount of information about a presumed underlying process. So for example, we could come up with the idea that instead of having these average sampling points here, we want to maximize the information by allowing individual jittering around these average sampling points. So we have some individuals observed a little bit earlier, some individuals a little bit later. So the yellow dots should be individuals. And already just visually, you can see that this allows us to better see that the underlying process is actually an oscillating process and not, for example, just a straight line. We're not changing the overall amount of information. That stays exactly the same, but we're having a different design which gives us more information. From a missing value perspective, that's a catastrophe because we're having variables with very few observations per individual in the wide format. Maybe only one observation, but it actually maximizes the information about the underlying process. And that's something I'm not just making up based on nice figures, but we actually did some simulation study on this. And the story of this simulation study goes like this, that we generated the damped linear oscillator with a 1 hertz frequency. We sampled out of this at 11 time points, 200 individuals. And because I've just seen that I have only 2 minutes left, what we found is that when we have average sampling intervals, which are well below the so-called Nyquist-Shannon criterion, everything works nicely. As soon as we have intervals which are a little bit longer, things break down. But as soon as we allow this jittering in the sampling intervals, we're in the position of nicely recovering the underlying true parameters. So again, this shows that we can make more out of our data and more out of our design if we think about how to best identify underlying processes instead of trying to get these nice rectangular data frames without any missing values. Last point, and I can do it in 1 minute, is I think better ways of integrating within and between person research. Here I just want to mention that we can use this continuous time modeling, for example, to fit dynamic factor models for 3 variables across 200 time points here with 100 measurement occasions. And these tick marks are showing that they're individually, or that they are varying over time. So we can fit these kinds of models. A structural equation model with quite a couple of parameters to be estimated and the single individual, but because we have time in here. And the cool thing is that now with structural equation modeling, we can, because we set this up in an SEM framework, we can begin to combine these within time series models with cross-sectional models. So we set up a single model for a given individual and a group structure, and this allows us to make specific comparisons. So for example, this would be an explicit test of what Peter Mollenaar in one of the earlier sessions here called ergodicity. So we can test for the equivalence of a between and a within person structure in a direct way via a likelihood ratio test. And that's something we can do for all person time point combinations, and for each combination we can test. So each dot here would be such a comparison. We can test whether we have structural equivalence or non-equivalence, also controlling for various background variables so that we can test for conditional equivalence. All right, so let me summarize. We have seen that there exist 2 different types of longitudinal models, depending on the role of time. We have static models and we have dynamic models. We have seen that even though dynamic models are extremely powerful when it comes to the identification of mechanisms underlying change processes, the way they're currently being used in much of our research is somewhat suboptimal. As I said before, maybe it doesn't make a big difference, then it's just slightly suboptimal, but it can make a huge difference, and then the parameters and their interpretation is really off. I introduced continuous time modeling as dynamic models that treat time continuously and thereby overcome these problems of discrete time models. And I've shown you a little empirical example on how to implement and interpret such continuous time models via the CTSEM package. And I ended with 2 conceptual points. One conceptual point is that just thinking continuous time may offer new ways to think about the design of our studies, and I try to illustrate that with the case of missing values. And I mentioned that we can model oscillation with it. And the second point is that it may help us to improve the ways we integrate within and between person research. And on the technical side, I just quickly mentioned that we can also use it for dynamic factor modeling, for example. Am I in time, Lars? Good.